Welcome back to the last session of today. So we have Mishra talking about parameterized algorithms. So we'll ditch approximation and try to solve things exactly again. Let's see if she shall succeed.
All right, thank you very much. I think the promise was to do parameterized approximation. We'll see if we get there eventually. But I thought it was a good opportunity to advertise parameterized algorithms as an alternate coping strategy for problems that are hard. I noticed that you've had a pretty intense morning session today, so we're going to keep this fairly porous and sort of lightweight. And well, if you've not seen parameterized algorithms before, you might find that things are conceptually new, but in terms of the technical aspects will mostly be cutesy. There are a lot of heavy hammers in this context as well, and you can find tons of resources, and I will share some pointers with the organizers. So if this works as a gateway drug, my job will be done. So hopefully you can go and check out more of the the heavy machinery in more advanced resources. But let's maybe start by talking about what are parameterized algorithms. And a key to this framework is, like the name suggests, this idea of a parameter k. I suppose, I don't know, is the font size too small for folks at the back? I'll try to maybe write a little bit larger. So how about something like this? Is vertex cover visible? Oh, that's all we care about. So, okay, good. So one thing that may be a bit of a cognitive switch is that we've been talking optimization in most of our settings. I'm going to switch back for a bit to a framework of decision problems. As you know, you can go back and forth between optimization and decision without too much difficulty. So this should be okay. So here we will think of our input as a graph G and a budget K. And the question is, does G have a vertex cover of size at most K? And vertex cover is a little annoyingly named, so in case a reminder is useful, a vertex cover covers edges, but the name probably comes from the fact that you're using vertices to cover edges. So for example, this covers these three edges out here. This one covers a bunch more. We still have one more uncovered edge. That's, hopefully that takes care of everything. Yeah, okay, so what's vertex cover? We've already seen multiple algorithms for vertex cover. In particular, we have seen a matching based to approximation, we've seen a LP doubling based to approximation, and we've also seen a primal dual based to approximation. And although we haven't talked much about, so the question that you always ask when you're designing algorithms is the question of, can we do better on any parameter? Can we do it faster? Can we get better approximation ratios and so on? Right? So there is, again, some machinery that we won't go into, but we have good reason to believe that you cannot get approximation ratio better than 1.32 or something, assuming that p is not equal to empty, and you cannot get better than 2, assuming slightly more, so assuming something called the unique Kim's factor. So this approximation ratio, it seems like you hit a bit of a glass ceiling. So although we have many ways of getting into approximation, it seems like you cannot, if you confine yourself to the land of what you can do in polynomial time, we have good reason to believe that you cannot improve this to approximation. You cannot improve the approximation factor. So what we're going to start thinking about is, what if we gave ourselves a little more flexibility on the time, then can we get better approximation ratios? Okay, so that's the question we will ask ourselves. And what kind of time luxury are we looking at? Well, if we are to be motivated by the kind of setup we have in the world of parameterized algorithms, the idea is to say that we want our algorithms to be, we sort of still mostly want them to be polynomial. The bulk of it is polynomial, but we are going to sneak in an extra factor, which is, some function of what we are calling a parameter. So now the question that you probably have is, what is a parameter? And the answer is that a parameter is something that you get to pick. So for once you're working with a problem, you can say that, well, I happen to be working on, I don't know, like networks, graphs that come from network topologies. Okay, so the kind of networks that connect, your LAN network sort of thing. You might say, well, my LAN type networks typically have low diameter. Okay, so I want to think about vertex cover, but through the lens of diameter. I want to parameterize it by diameter. I know that all the graphs that I'm working with in my application, they all have small diameters. So if I could get an algorithm which was exponential in the diameter of the graph, but polynomial in its size, okay, let's say you're only working with constant diameter graphs. Actually, you can push this all the way up to what? For the running time to be overall polynomial, I need the diameter to be bounded by. So I want to say something like, as long as the diameter is at most blah, this is exactly right. So log n. Okay, so it says log base 2 will cleanly cancel out, but asymptotically you don't care which base, right? So as long as the diameter is log in the size of the graph, right, this overall running time is going to still be polynomial. So in some sense, you've devised an algorithm which is pretty good for graphs that are low diameter, right? And this is sort of the advertisement for this framework, is that once you say that you're targeting this kind of a running time, it makes you think different, basically. You start thinking about it from the point of view of, okay, how do I now? Now, it definitely feels like you're more elbow room in terms of the running time, because you allowed exponential complexity in the diameter. And although we are getting polytime algorithms for vertex cover for an attractive class of graphs, all graphs that have low diameter, doesn't contradict the NP hardness, because there are indeed many graphs that have diameter omega n. So, this is worst case exponential, but now the cases where its running time is nice, you can kind of identify what these graphs look like, and that's kind of nice to know, okay? So you can puzzle about whether you can come up with such an algorithm for vertex cover. You're going to work with a more obvious sort of a parameter, which is what is usually called the standard parameter, because it's inspired by something that comes straight from the problem. So the standard parameter is k. Okay, it's the size of the solution. It's the size of the vertex cover you're looking for. And vertex cover, especially being a minimization problem, it's reasonable to assume that in most application contexts, you're looking for small vertex cover. So the budget being small is a reasonable assumption to make. Okay. So of course you could, again, the parameters, there are two sort of criteria for picking parameters. One is that hopefully you can sell it in the marketplace, right? You can say, look, I've chosen a parameter which is actually small for the kind of inputs that you're looking at. So it should be useful for you, because my nice algorithm is going to actually handle all of your inputs in polynomial time. So the sellability in the marketplace is one criteria for picking a parameter. But the other criteria is, of course, the parameter should be useful in that it should give the algorithm designer enough leverage to actually make algorithms that look nice from this perspective, right? So, so just as a sanity check, assuming that we are familiar with the graph coloring problem, so let's say we are interested in, so in graph coloring, again we have G and K, and I want to know, can G be properly colored using K colors? So if you haven't seen the notion of a proper coloring, this is basically the same as asking, can you partition your graph into K independent sets? Okay, at most K independent sets. And let's say I want, I want some C to the K poly n algorithm for this problem. Um, would you expect to be able to design such an algorithm based on, okay, this is a bit of a sad question for people who haven't encountered k-coloring before. So what we know about k-coloring is, does anybody know what 2 coloring corresponds to? When k is equal to 2, that's checking if a graph is bipartite, and that is something we know how to do in polynomial type. Okay, so that's actually a reasonable special case. What about k is equal to 3?
We can guess the color for one and then do bipartite for the remaining.
Okay, that's an excellent algorithm. What you can do is, if you're willing to spend 2 to the n time, what you can do is you can guess the first part. Okay, you say, okay, I don't know what this first part is going to be, but for every choice of the first part, you can check if the rest of the graph is bipartite. Of course, you can first check if the graph is bipartite, you're immediately done, but if it's not bipartite, then what you can do is you can try to basically guess an independent set, but notice that this is exponential in the size of the graph, which is a little bit different from what we are looking for. But before getting into algorithms, I just wanted to confirm that hopefully most of you have seen that 3 coloring is an NP-complete problem. If you haven't seen this before, then just take it on faith for now. So determining if a graph can be partitioned into 3 independent sets is one of the classic NP-complete problems, right? Now, in view of this, do you expect to be able to design an algorithm with this kind of a running time? In fact, let me up the stakes and ask if, so do you even expect to have an algorithm with this kind of running time, which is, it's still polynomial for fixed k, right? So if your parameter is a constant, like maybe not log n, but if your parameter is a constant, it's still polynomial, okay? But that's also precisely the problem, right? So do you see why you don't expect an n to the k algorithm for k coloring? Yeah, sorry, I think some of you are articulating it already, so does somebody want to spell it out? Because 3 coloring is NP-complete, and so if you plug in k is equal to 3 here, you get like n cubed. So even if I make this asymptotic, order n to the k, order n cubed for 3 coloring is highly unreasonable, right? So not only do you not expect this sort of a running time, you don't even expect this sort of a running time, okay? This is more freedom in the running time, okay? This is a little bit less, because here the poly n is, irrespective of what k is, the poly n is a fixed poly n, okay? And as k varies, basically it's the kind of constant overhead that's going to change, okay? With n to the k, as k varies, the polynomial also varies, right? So if k is 3, you have n cubed. If k is 4, you have n to the 4th, and so on. So it's not as nice anymore. But even if you up the stakes and say I give you so much time, even then something like k coloring will not have this nice algorithm. And the hardness of that just follows from NP-completeness. So it's not, so not every parameter is a good parameter from an algorithm design point of view. You could pick a parameter that's just really annoying. Like for k coloring, k is not a good choice of parameter because it's not going to get you anywhere. But for k coloring, you can use other parameters. For example, you could try parameterizing k coloring by vertex cover, because why not, right? Well, one reason why not is because this parameter might be hard to compute, right? So given a graph, like I don't know how to find an optimal vertex cover, but you know how to find a two approximate vertex cover. So if the graph has a small vertex cover, you can still find a smallish vertex cover, and then you could ask the same question. So can I design an algorithm whose running time looks like this, okay, for optimal coloring? So now I want to know what is the smallest number of colors that I need to color my graph. And this is a nice thing to try and work out, because The vertex cover gives you like this one big independent set already. And then the vertex cover itself is kind of smallish, so maybe there are things you can do, okay? So I don't really mean 2 to the vertex cover, but so you could be like 4 to the vertex cover or something, but this is fine, okay? So this is like maybe something to think about. But yes, the idea is that for a given choice of parameters, so like I said, the standard parameter is the first one that comes to mind. It's the thing that you're trying to optimize is called the standard parameter. But you could use your imagination to come up with other parameters. And the thing that you're trying to balance is the utility of the parameter for 2 sets of people. The first group of people that is the people you want to sell the parameter to. I'm going to say, look, in your situation, this parameter leads us to a nice class of instances that can be solved nicely. But the other people that should find the parameter useful is the people who are making the algorithms. The parameter should give you enough algorithmic leverage. Okay. All right. So let's try to think about vertex cover parameterized by the standard parameter, and let's see what we can do with that. So we're going to come up with hopefully a few different algorithms that have like a running time of this form, and hopefully they'll get progressively better, not progressively worse. So first, since we're doing approximation, let's say that you have polynomial time, so you might as well get an approximate solution first, right? And then see if from there we can solve this decision problem. So we run the approximation algorithm, and let's say the approximation algorithm, so let's run your favorite 2 approximation algorithm for vertex cover, and let's say this guy outputs some subset of vertices. Now if the size of this subset is strictly bigger than 2k, then what can you say? We are solving a decision problem, and the approximation algorithm has given us at most twice opt. The answer will be no, because if there was a vertex cover of size at most k, surely opt is at most k. So twice opt would have been at most 2k. But what's returned by the approximation algorithm, so hopefully not a buggy implementation, and what's returned by the approximation algorithm is more than 2k, so we can say no. Okay. So it's reasonable to assume that we have a vertex cover of size at most 2k, because we have dealt with the other case. And now notice that you have this f of k freedom, okay, and you have this big graph on the outside. So this is the unbounded portion, n minus 2k. Now you want to know, is there a vertex cover of size at most k, and you have time. The time that you can exploit is any function of k that you want, right? 2 to the k, 4 to the k, 10 to the k, 100 to the k, take your pick. So what would you like to do, given that now the approximation algorithm has given you a nice picture of the graph, right? So this vast ocean of vertices, but they're all isolated, okay? And then there is a little bit of junk on the top, but it's bounded, right? So the interactions within those 2k vertices and the interactions across can be really complex, but all that complexity is centered on this small part. So can you leverage that there? On the small part, you can sort of afford to brute force. Okay. So how will you brute force here? So we were talking about guessing when we were doing pre-coloring. Is there something that you can guess here? Belongs to the thing that we are looking for, right? So this is S, and I can try all possible subsets of S. In fact, I don't even have to try all of them because some of them are too big. I'm looking for a vertex cover of size I'm looking for a vertex cover of size at most k, right? So, this, I don't know if blue is going to be visible, but this mystery vertex cover, the one that we're looking for that we don't see right now, okay, the algorithm doesn't know where it is, but if there is one, the size of this mystery vertex cover is at most k, okay, and maybe let's call this mystery vertex cover, let's label it T. So what we can guess is, we can guess the intersection of T and S. So we can say that, well, the approximation algorithm picked a few vertices, right? Okay, it picked some vertices from T, which is the one that I'm looking for. I don't know which ones, and maybe the approximation algorithm was completely off. It didn't pick anything from the thing that I was looking for, fine. But we're looping over all possible things, right? And this loop is going to cost us, how much is this guess going to cost us? It's going to cost us 2k choose J, J going from 0 to k, right? All subsets of size at most k, right? I mean, if you're lazy, you can just say 2 to the 2k because at most all possible subsets, but okay, if you want to be careful, then you can work out that's. Alright, so, but it's definitely like some f of k, okay? So right now I'm not worrying about optimizing the f of k, I just want to get some algorithm that looks nice, okay? That has this format.
If
Yeah.
the goal is to say that whether there exists a vertex size, vertex cover of size less than or equal to k.
Right.
Why can't we just choose like 2k choose k rather than summing over j equal to 1 to k? Because if you could find a vertex cover of size a, then that would be sufficient, right? So why are we summing over?
Right, because yes, it's a good point. The thing is, what we're trying to guess is where does the vertex cover that I'm looking for, where does that intersect with S, okay? And the thing we're looking for has size at most k, right? So it could intersect with S at, like, let's say you're looking for a vertex cover of size at most 10, and you have the set of 20 vertices, right? There is no guarantee that the optimal 10 vertices is a proper subset of this guy. The optimal set is going to, in general, look like I picked something from here and something from here. Right? Now, so I can basically say, okay, my optimal mystery vertex cover, okay, like how does it look with respect to this partition that we can, so this partition of S and B minus S we found in polynomial time. It has the special structure that S is small and B minus S is big but it's independent, so it has nice structure. It's big but it has nice structure. The part doesn't have structure, is small. So it seems like a win-win, right? Now the thing that I'm looking for is somehow partitioned across these two sets, right? So these blue vertices that I'm looking for, some of them are in S and some of them are in B minus S. And B minus S I cannot guess, okay? That's too expensive. That's like n minus 2k choose J or 2 to the n, like I cannot guess. This is too big, okay? But at least here I can guess, okay? And hopefully it's clear why we are looping, right? Because we don't know how many vertices from the mystery vertex cover land up in S. It could be any number. In the worst, I mean, I don't know if I should call it worst case, but it could even be that S completely messes out on D, although that would be a very special case, but yeah. So that's why we have to do that loop, right? Okay, so let's now fix a guess and see what we can do with it. So now we are saying, well, suppose we are in this specific parallel universe where we firmly believe that T has picked out exactly these vertices from S, okay? And we hope to build this out to the rest of T, which we like, you know, if I know that from S I'm precisely picking these vertices, what else should I pick from outside to complete this to a vertex cover? Sorry, yes.
Sorry, I'm not
Yeah.
class actually. Can you just repeat the algorithm just once?
Okay, sure. The algorithm starts off by running your favorite 2 approximation for vertex cover. That gives you some set of vertices. If that's too big, you can say no, right? Because that's, if S is more than 2k, there's surely no vertex cover of size at most k. So now you have a subset of at most 2k vertices that forms a vertex cover. So this is at most 2k, so this is at least n minus 2k. This part is an independent set, and this part is a vertex cover. And so what we are looking for right now is a vertex cover of size at most k. So I'm saying this thing, suppose we have a yes instance, okay? So then this thing I'm looking for, let's call it T, and let's just do an exhaustive search for T, okay? And that exhaustive search will hopefully cost us running time in this format, so it's not going to be completely exhaustive. It's going to be exhaustive in how it appears in S. So we want to ask this mystery word. So you're looking for something. If all of our guesses fail, then the thing we're looking for doesn't exist. That's the sense in which it's exhaustive, right? So we're looking for something. We don't know where the vertices of T are, but S is a very small window that I have. So within S, I can just say, okay, what was S intersection T? I still don't know, but I can try all possible subsets. So that's what I'm doing. And I'm saying this is a for loop, right? So I'm saying, well, let's take a pause and let's look at one iteration of that for loop, and let's see what to do if I have guessed that my mystery vertex cover picks exactly these vertices from S. Okay, what can I say if that is supposed to be the case? In particular, just as a sanity check, let's think about what's going on in S minus S intersection T. So can I have an edge here, for example? If T picks only the blue vertices from S, and T is additively a vertex cover, right? So then can we have an edge sitting here? No? No. Because how is T going to cover this edge? We have expressly forbidden T from picking any of these as per our guess. Okay? So if this guess gives you an edge outside, like this, nonsense guess, just skip. Okay? There's no need to bother with it. So this is a prerequisite for this guess to be reasonable. This portion has to also be an independent set. Okay? So now T is covering some edges. It's covering all the edges inside the blue region. It's also covering all these edges coming out. All the edges that have at least one endpoint there. It doesn't have to worry about covering any edges here because there are no edges here. So what are the edges that we are nervous about? Yeah, from the red to the rest. Okay. Now these edges were being previously handled by S, but now you've kicked out these vertices from the vertex cover. So unka kaam kisi ko to karna padega. Okay. But now an edge can only be covered if it's not covered by this endpoint. It has to be covered by the other endpoint. Right? We don't have a choice. There's no optimizing to do here. We are just forced, right? So everything that these guys were doing, okay, so all of these edges are now stranded, and we just have to pick everything here. Okay. All right, that makes sense. So think of this as like the shadow of the red part. Okay. Whatever edges the red part was covering, you have to go to their other endpoints and pick all of them, because if you don't, then you're not even a vertex cover. So this part plus this part is our new vertex cover. Okay? And once we pick these, which we are forced to do, we now have a vertex cover. Now the only question is this T at most K or not? Okay? So that's just something that we have to count and check. How many did we pick from here? How many did we pick from here? If we pick at most K, then we can stop the outer for loop. We can say we found our vertex cover of size at most K. But suppose none of these guesses work out, right? With all of these guesses, the shadow was bigger, like it was too big. So, maybe we threw out 10 vertices and we ended up picking 7. It's not good enough perhaps, because, that's just, you need to be, whatever. I mean, this is, let's say, if it helps to put some numbers, we can put some numbers. So let's say K was 10. So this is a collection of, let's say, 20 vertices, right? And in this case, we have thrown out 10 and we pulled in 7, okay? So then we are getting 10 plus 7, which is kind of useless, okay? So that doesn't work. So yeah, basically just do what you're forced to do, okay? So overall what's going on here is, this is brute force search for the intersection of the mystery vertex cover inside the approximate vertex cover. Once you fix a guess, everything else is fortunately forced. Okay? This may not always be the case, but vertex cover is a super special sort of a problem. So here everything is forced. If you were doing some other problem and applying this sort of a framework, usually this is the step where you will have some more work to do. So usually some kind of branching or dynamic programming or some nonsense. But here, fortunately, everything is forced. It's a one-shot thing. Pick these fellows, check if it's at most K. If it's at most K, you're done. Otherwise you move on to the next guess. And if you've exhausted all your guesses and you are not done anywhere in between, then you can report no. You can report no because of the exhaustiveness of this thing. The correctness argument is that agar there was some vertex cover of size at most k, it would have manifested somewhere in this for loop, right? You would have caught the correct guess, and then since your hands were tied, everything was forced, that vertex cover should have emerged as a solution when this algorithm was trying to find it. Okay? So the correctness is by exhaustiveness. Now in terms of running time, how are we doing? All of this is some poly junk. The main overhead is in this. You can go and actually, compute that sum, but I'm going to loosely upper bound it by it's no more than 2 to the 2k, so 4 to the k. It's some function of k. We are going to improve this in a second, so that's why I don't want to waste my energy on that. So okay, we're going to okay, so we'll improve this in a minute. Again, in some contexts, it pays to be careful about like the analysis, but we are going to do better. So okay, so one way that we can improve this right away is if we had an additive, yes, question. Is it the guessing time k to the k? Well, that's because you're looking at the extremities here. This one's maximized probably at 2k choose k. And you can upper bound this by k times 2k choose k, which is 2 by k to the
Some
k.
of binomials coefficients is 2 to the 2k.
Yeah, well, okay. So, but these are like binomials, but not all of them, right?
So it's bounded above.
It's bounded above is what I wanted to say. Yeah, bounded above is like, I'm taking only certain collection of subsets. If you do all subsets, it's 4 to the k is what I was saying. So, yeah. Yeah, I was trying to, probably there is, I don't know, the k to the k is probably coming from some intermediate bound that you're thinking of, but you can just easily upper bound this. So, okay, good. Alright, so where are we? Okay, so one way to straight away improve this running time is if I didn't have to do 2k choose k, but instead, like if the set I was guessing from was smaller, okay? So if I was very lucky and somehow instead of a 2 approximation, I had an additive plus 1 approximation, I'd be very happy, right? Because then it's like 2 to the k more or less. 2 to the k plus 1, okay? So I can try, again, upper bound by all subsets. But now all subsets of a k plus 1 size subset is 2 to the k plus 1, so asymptotically 2 to the k. So that's an improvement. That's an improvement right away if we could work with a plus 1 approximation, which we don't have. Okay, all right. So we are going to proxy this plus 1 approximation by a technique called iteration. It's very simple. So so here's what we're going to do. We have the whole graph G, and I'm going to start off with any k plus 2 vertices. Okay, so this is a subgraph, let's call it H naught perhaps. So these are my favorite k plus 2 vertices from G. Does this have a vertex cover of size k plus 1? Sure. Any n vertex graph has a vertex cover of size n minus 1. And there are graphs of size n that require vertex covers of size n minus 1. For example, the complete graph on n vertices, you have to pick everything except for 1. Okay. Alright, so any graph on n vertices has a vertex cover of size n minus 1. So if I pick k plus 2 vertices, I have a vertex cover of size k plus 1. And then I do this whole thing with this silly vertex cover of size k plus 1 and with one vertex sitting downstairs. Okay. And here, if I run my 2 to the k algorithm and it says, boss, I couldn't find a vertex cover, then what can you do? This total graph, you couldn't find a vertex cover of size at most k. So will your whole graph have a vertex cover of size at most k? No. Okay, and it's good to be careful about such things because there are problems for which this statement may not be true. But vertex cover has this property called hereditariness, okay, so which means that if the big graph had a vertex cover of size at most k, you could project this vertex cover on any subgraph and that projection will be also a vertex cover of that smaller thing. Okay, so if the big graph had a vertex cover of size at most k, you could basically by projection argue that the smaller graph would have also had a vertex cover of size at most k. So if you're not able to find a vertex cover of size at most k in this Chindi graph, you can say no for the whole graph. Okay, that's a safe thing to do. Otherwise, you have actually found a vertex cover of size at most k. Okay, and now there are two vertices sitting outside. So this worked, yay. So now pick your next favorite vertex from outside and bring it in. And where are you going to bring it in? This was a vertex cover of size at most k. So I'm going to bring it into this, and now this is a vertex cover of size k plus 1. Now repeat the whole drama and try to get a smaller vertex cover. And if it works, that's awesome. You can bring in the next vertex and you keep going. If you survive till the very end, then you're done and you found a small vertex cover. If you get stuck somewhere in between and you have to say no, then you can freely say no for the whole thing and avoid the whole algorithm. Okay? And you're done. Okay, so what we have saved is from 4 to the k, we have gone to 2 to the k. We paid a price in the polynomial running time because this whole 2 to the k plus 1 drama we are now doing n minus k plus 2 times or something. Okay. So at most n times, so n times 2 to the k, and then some poly overhead for some counting business, because for each of these guessed iterations, you do have to do some counting to check what is the size of the neighborhood, so there's some poly overhead coming from there also. So another n, we don't care. I mean, for now we don't care, okay? So like a lot of people break their heads about optimizing the n part of the running time as well, like the function of n. But for now it's like it's all poly for us. So those are trade-offs that people really care about sometimes. Like, you know, you want to optimize the f, you pay a price in n, or maybe you want to sometimes get a linear time algorithm, so you pay a price in the f. And if you can dominate both, then of course that's awesome, but rare. So, okay. Oh, okay, so once you have, so far so good, right? So the first k plus 2 vertices, okay? If you get a vertex cover of size at most k, then in the next step what I'm going to do is, so I have this rank list of vertices. It's really not a rank list, but you know, just some ordering of vertices, okay? So I've picked out the first k plus 2, and for that first k plus 2, let me just draw. These are the n vertices. So pehle to for the first k plus 2, we found a vertex cover of size at most k. And then I'm going to pick the next vertex in this list. And what I'm going to do is I'm going to pull it into the spotlight. And I'm going to say, you go and join the current vertex cover that I've found. The current vertex cover is always at most k at the end of an iteration. So if I pull in one vertex, then that vertex cover expands by one vertex. So it becomes a vertex cover size k plus 1. Now I do my brute force. And I try to compress it to a vertex cover size at most k. So if this compression succeeds, then I move on to the next step. So I pull in, okay, I pull in the next vertex, and I keep doing this. At some point, maybe when you've pulled in this vertex and you try to compress it, the compression fails. It says that, look, at this point, I cannot make this vertex cover smaller, but then that means that this subgraph doesn't have a vertex cover of size at most k. But if the subgraph doesn't have a vertex cover of size at most k, the whole graph does not have a vertex cover of size at most k. Okay. So, sorry? You can pull in 2 vertices at a time if that's what
The 2 vertices that will push down. And then you bring the new vertex in.
Right.
Will it ever like?
Yeah, they might go back. I mean, yeah, there may be a song and dance that happens here. Like, these are not fully committed to being outside.
Yeah.
So depending on, like, when somebody comes in, if it turns out that, like, as I pull in more and more vertices, this fellow is more, like, maybe to begin with, in my first k plus 2, this was an isolated vertex. But maybe when I bring in the last 3 vertices, this guy is covering 3 edges. So at some point, this may go back into the optimal vertex cover.
So like the 2 to the power k comes from checking all subsets.
Checking all subsets at each iteration.
But
Yes.
then these ejected 2 vertices, like that we've thrown out.
Yeah, the vertices that are getting thrown out, like the thrown out region is constantly expanding. So to begin with, it was 2. After the next iteration, it will be 3. So if you have successfully survived, let's say, root n iterations, then the size of the thing outside will be like root n minus k plus 1.
Okay, so you can stop after that.
No, we never stopped, because notice that this brute force algorithm that we did never touched the outside. Like, it never did any brute force on the outside. You're always doing the brute force only on the vertex cover.
Okay.
Like, so that's why we are really struggling, and I mean, we're really being careful about keeping this part small.
Okay.
Right? So we are compressing and we are carefully injecting one vertex at a time, and we never inject too many vertices into the vertex cover together. We add one vertex and then we run what you can think of this as a compression subroutine. Right? So it takes as input some graph with a vertex cover of size k plus 1 more than what you want, and then it does this all subsets and swapping and all of that to figure out if you can use this k plus 1 size vertex cover as a guided search towards a k size vertex cover. And if this guided search does not succeed, you know that there is no k size vertex cover and you can say no. So in every iteration you are carefully expanding the vertex cover from k to k plus 1, compressing it back to k, then expanding to k plus 1, compressing back to k. And as you keep doing this, what is on the outside is of course growing.
Yeah.
And the set may also change. Yeah.
My question is like, so we bring the new vertex in, like, is there a solution with the vertices that you've removed that you're not considering?
Well, no, because what you're going to do is when you bring the new vertex in, you're going to run this whole algorithm again, right? So you're going to try all possible subsets of this k plus 1 size set.
Yeah, the k plus 1 is fine, but what about the...
Right, so if you remember how we did the guessing, we said that, okay, so suppose we pick these guys in the guess, then the entire neighborhood of everything that we did not pick will be on the outside and they will get chosen. So they are going to get pulled up. So in that swapping step, they are going to get pulled up. And whenever that's optimal to do, you do it. Yeah. So the texture of the vertex cover that we are maintaining may change quite a bit as we go along. Yeah.
What are the other requirements for us to use this technique in other problems?
Right. So mainly I think it's a good question. And mainly I would say that something like hereditariness is a sort of an important thing. Because you want to be able to say that whenever you say no at an intermediate stage for a subgraph, you want to be able to say no for the entire thing. But I think there are at least a couple of papers where they managed to somehow use this technique even for non-hereditary problems by being careful about other things. And in general, what is happening is that you are solving. So if you think about like the problem that you are actually solving after you make the guess, so notice that what you have is an independent set on top and an independent set on the bottom. And there are edges going across, right? And these vertices are actually forbidden, so you cannot pick these anymore because of the guess that you made, right? And now you're looking for an optimal vertex cover here with these vertices being forbidden, so now it should be really quite obvious that you just have to pick everything on the other side that's not isolated. But in general, let's say you were doing something like this for feedback vertex set, right? So feedback vertex set is remove vertices so that the graph becomes acyclic. The resulting graph is a forest. So you can go through essentially the same template, like practically like a formula. What you will end up with is this is a forest, you cannot pick anything from here, and all the cycles are going across. Okay. So now you have to pick an optimal collection of vertices from the bottom forest to kill all cycles going across. And it turns out that that problem is actually NP-complete. So this intermediate compression problem can sometimes be NP-complete, but because we have, overall FPT running time in our hands, you can still do this by some branching and you can still do it. So it isn't really like so in fact there's kind of an interesting paper which says that, so this whole method is called iterative compression, hopefully for obvious reasons now, because you're iterating and compressing. So every time you are making this k plus 1 size solution smaller, that is what you're calling the compression routine, and since you do it n minus k times roughly, that's the compression is being kind of there's an iteration loop that goes around the compression to solve the whole problem. So it's actually like it's kind of great that you're able to see that it's kind of a broad framework. You can use this, you can try using this for your favorite problem, and indeed I think there are a handful of problems for which iterative compression as a technique actually gives you the best known running time that you know as of now. So it is a powerful technique. And there is an interesting paper which basically says that vertex cover and I think cluster vertex deletion are the only two problems for which the the compression problem is doable at polynomial time. It's one of these Yarakaki style meta theorems which says that for any other subset type graph problem, the compression problem, these are called the disjoint instances, because essentially what happens when you do this guessing business is you're left over with some forbidden piece on one side and a disjoint piece on the other side, and all the forbidden objects that you're trying to that you're trying to get rid of. For vertex cover its edges, for FES its cycles, for OCD its odd cycles, and so on. So for these special class of problems where these are subset problems which are trying to hit a class of forbidden objects, essentially for cluster vertex deletion you're trying to hit what are called induced paths of length 3 and so on. So, so there are only two problems for which the compression problem can be done in polynomial time. For all other problems, for all other problems in that setup, the compression question is actually empty complete. So, but usually you can still do something and be within an overall FPT running time. So that's the only general meta theorem that I'm aware of. But I don't know that you can look at a problem and immediately anticipate if iterative compression will work or not. So every problem is its own story. But typically I think it's been applied to subset problems where you're trying to hit, like there's a set of objects that you're trying to get rid of. Although again, there are certainly exceptions in the people who have used iterative compression for other things as well. But in general, I think it's a really cute technique. I mean, the idea is that on a small subgraph, you'll almost always find a trivial solution that's just tantalizingly close, like one off from what you want, and you can typically do some nice brute force to compress it, and and then you just keep going. So that works, and in terms of running time, like I said, we paid a price of an extra n factor outside, but we were able to improve from 4 to the k to 2 to the k, so that's a sort of bit. Okay, now let's see if we can get a direct 2 to the k algorithm, because we've seen 3 approximations for vertex cover. I feel like we should give at least 3 parameterized algorithms for vertex cover as well. So, in fact, we should see 2 more because these 2 algorithms are basically the same thing, so we should probably do a couple more. Let's see. Okay, how are we doing for time? Okay, let's do a branching based. Okay, this section of the board is getting a lot of abuse. Okay, so let's try to come up with a recursive approach to doing vertex cover. Okay, so we are now not going to, we're moving away a little bit from this kind of iterative compression framework. And our goal here will be to get, again, a 2 to the k sort of an algorithm, 2 to the k or better. So, okay, so the goal with vertex cover is to cover edges. So let's say I have an instance of vertex cover which looks like g comma k. And of course, it's going to be like some base cases whenever you're doing recursion. So if g is empty and k is non-negative, then you can say yes or no. G is empty and k is non-negative, you can say yes. G is non-empty and k is at most 0, you can say no, because you have an edge and you don't have budget. So if you have an edge and you don't have budget, then say no. If you have no edges, you can say yes. Okay, so those are like corner cases. So now G has at least one edge and at least some budget. This is the interesting situation. So since G has at least one edge, let's pick an edge UV. Now, the tricky thing is, of course, I know at least one of U and V are in my solution in any vertex cover, but I don't know which one. So, which one should I pick? So if you're a randomized person, you'll say, let me toss a coin, which you can totally do. That's a legit randomized algorithm for vertex cover. But we are currently not randomizing, so we are going to do parallel universes. So say in one parallel universe you're going to pick U, and the other parallel universe you're going to pick V. Okay? So these recursive universes are going to be, well, I've picked U, and I've picked V. And what's my budget now? K minus 1, because I've used up one vertex in each case. Okay. Okay. So that's 2 parallel universes with a reduction of 1 in the budget. And now I can keep going until I hit the base cases. So what is the depth of this recursion tree? K. Because if you go any further than k, you run out of budget. At that point, you can stop. And what's the branching factor? at every node branches into like how many sub-instances does it spawn? Every instance spawns 2 sub-instances, right? So what's the total number of leaves in this recursion tree at most? 2 to the power k at most. Okay? At most, because some of these branches may die off early. If you're able to cover all edges and fewer than k vertices, then you have some lucky stops earlier, but at most you're going to get 2 to the k leaves. Okay? And the amount of work that you do at each node of this recursion tree is certainly polynomial, because you just have to choose an edge, and you have to observe what happens when you delete an endpoint, and figure out these new graphs, g minus u, g minus v. All of this is a polynomial amount of work. And at any leaf, at any point where you stop and you say yes, because you have run out of edges before you ran out of budget, you can always walk your way up the tree to the root and reconstruct your solution. Like basically look at what choices did I make, which parallel universes did I step into, and so on. It's a nice exercise to check that this actually also enumerates all the minimal vertex covers. Not all vertex covers, but all the minimal vertex covers, size at most k. But anyway, so this is a 2 to the k poly algorithm. Sorry?
Can it count a vertex curve which is not minimal?
Can it count a vertex cover which is not minimal? I think at all the leaves of this particular tree, I think you're going to get only minimal vertex covers. I think so. So if you have vertex covers of size at most k which are not minimal, this algorithm may not find them, or will not find them, I think. Okay, so yeah, okay, so let's see. I mean, okay, actually the only guarantee I want to make is that every minimal vertex cover size at most k is certainly enumerated. And there may be non-minimal vertex covers of size at most k that are excluded, but there may be some non-minimal vertex covers that do get caught. So that's possible. But I think you can definitely come up with examples where, like, I cannot guarantee that every vertex cover of size at most k is caught here.
At every stage we are choosing an edge and then we are choosing both the sets of edges,
Okay.
right? So the number of branches from a single node would be like 2e.
Just 2, because at every stage what you're doing is you're picking one edge and you're branching on its endpoints.
So let's say we are at step I level.
Okay.
So we still have n minus I edges, or like n minus
Right.
some
So let's
f of
do
edges.
u, v, w, x, y, z. That was not very smart. Let's see. What comes before u? D, I guess. Okay, alright. Okay. So yeah, so let's say we branch on UV, right? So we are going to get like 2 graphs. So when you pick U, you delete U, which means you also delete all the edges incident on U. And so you're going to get this graph. If you delete V, you're going to get that graph, right? And then in those parallel universes, what that looks like is, well, in one you're going to get this guy, and in the other you're going to get let's see, I'm going to get this guy. So then now in this universe, you can again pick your favorite edge to branch on. So when you do this, you're going to get like.
So we pick any of the edges that. Like,
yeah, you pick any of the edges. So yeah, pick some edge. So now like you look at it like just think of this problem afresh, right? So I now just have a smaller instance of the same problem, right?
But we are not exhaustively searching over all possible ways of. I mean, if we had chosen every possible edge and then branched, then
No. Yeah, no, that would have been an M-way branching. We don't want that. Yeah, no, right. So the edges are. So if you're worried about like is every edge getting accounted for in some sense, basically what we are saying is intuitively what's happening is as you're picking vertices, you're knocking off a bunch of edges. Like along with the vertex, out goes all the edges that are covered by that vertex as well, right? So that's kind of an important thing to keep in mind. And if you think about like, okay, so maybe let's actually argue the correctness. So suppose there's a leaf which says yes, right? I want to argue that if you take, so every node has a unique parent in the tree. So if you walk up this tree and pick all the vertices that were picked at those nodes, you will end up with a vertex cover. And the main idea is to say, well, suppose not, right? So suppose some edge was uncovered, then that edge would have survived till the very end, right? Because it's not covered. And then it wouldn't have been a base case because some edge.
Like if after exhausting all k budget,
Mhm.
none of the leaf nodes answer yes,
Okay.
if all of them answer no, it does not imply that the answer is no, right?
It should. So, okay, so there are two, that's a good point. There are two directions to the correctness. One is to say that if there exists a leaf that reports yes, then we are done and we say yes. Otherwise, it's safe to say no. Okay, and let's think about why. Okay, so this is reasonable. If there is a leaf that says yes, then if you mimic all the choices that were made to get to that leaf, you should have covered all the edges, because if you didn't cover an edge, that edge would be present in the leaf instance and wouldn't be a leaf anymore. So either you have budget and you would have continued branching, or you don't have budget and you would have said no. There wouldn't have been a leaf which said yes. Okay, so that's fair. I think this part is fair. Now, why can we say no? Because, well, suppose you say no and the graph was actually a yes instance, right? So you have a vertex cover size at most k. Now I ask you, well, you must have covered UV. Which one did you pick? Okay, and you could have picked both, in which case I'll take any of the branches, doesn't matter. But you must have picked at least one, so you're going to guide me through this branching, right? And we should stop at a place which says yes, which contradicts our assumption that every leaf said no. Yeah, I think it's really not a terribly deep thing, I think. Okay, so you pick the first edge. You, as a responsible vertex cover, must have picked one of these endpoints. So I'm going to ask you which one. You say U, I say okay. Let's now look at G minus U, right?
No.
So you covered all the edges incident on U.
So all the leaf nodes answer no, which means that they are not vertex covers themselves.
Right.
So there exists a few edges which we have never seen.
Sure.
Let's say nodes A and B were never chosen across any of these places.
Right.
So, but every optimal vertex cover has A or B in it.
Correct. But every optimal vertex cover is also obliged to cover all of these edges as well, right?
Correct.
So so all of those things that you're saying are true, but let's just follow the pathway, right? Because an optimal vertex cover, all optimal vertex covers may be picking things that we have not seen, but they must also pick one of the endpoints of the things that we have in fact seen, right? So you have a vertex cover, and I'm going to use your vertex cover to guide me through this recursion tree, right? So you covered whatever it covered, and then I'm at G minus U, and at this stage I would have picked some edge that was available in G minus U, and I know that in your vertex cover, U is not enough to cover like this edge PQ, so your vertex cover has the obligation to cover PQ, so it must have picked at least one of these. So whatever it picked, I'm going to go down that path, right? And this is like one of those interactive fiction games, right? You keep telling me what to do and I'll go down that path. And at the end of the story, it must be a happy ending because you supposedly have a vertex cover, but that will contradict this assumption. Okay. Alright, so thanks. I think it's good to actually argue that this was correct. And hopefully the running time is also reasonably clear. So this is essentially exhaustive search, but pruned by the size. This is why it's useful to look at the decision version of the question in this context, because if you're looking for optimal, then you don't have this kind of clean stopping criteria. Okay. Alright, now given how much time we've spent, I will not do the fourth algorithm that I was threatening you with, but the idea is, the idea is instead of branching on edges, why don't you branch on vertices, right? So either V is in the vertex cover. If V is not in the vertex cover, who is in the vertex cover? All the neighbors of V, right? So this gives you a nice branching factor, because if you have high degree vertices, in one side you're losing one, but in the other side you're losing the entire degree of V, which is great. So as long as you have vertices of degree at least 2, you're going to get like a 1-2 branch. If every vertex has degree less than 2, what sort of a graph do we have? Every vertex has degree at most 1. Yeah, even in a chain you have like vertices of degree 2. So you actually just have isolated vertices and matching edges, right? So matchings, and so this is an easy base case to solve it directly. But in fact, you can upgrade to chains. You can say, well, I'm going to be greedy now, and I'm going to say, well, if my vertex has degree 3 or more, I will branch. And I cannot find vertices of degree 3 anymore, so every vertex has degree at most 2. Every vertex has degree at most 2. Now it is chains. It's paths or cycles. Paths or cycles also you can solve by hand. Okay. So you get an even better branching factor, which is like 1, 3. And you might be tempted to do 1,4, but now you have to kind of hold your horses because vertex cover is anti-complete on graphs with maximum degree at most 3. So now it's not so easy anymore. So 1,3 is kind of the limiting case of this style of branching, but you can do like some 45 pages of case analysis to get better algorithms, which people have done. So the current best known algorithm is something like, don't quote me on this, or this is somewhat on the record, so something like 1.27 the k, and then some poly m. Okay, so this is the best known. And I think there are some really passionate people who continue to attempt improving these running times. So it's there's a FPT wiki that maintains a race table for popular problems, and vertex cover is the favorite baby of the parameterized community. So it's a very long table of races for dedicated to vertex cover and its variants. Okay, all right, so cool. So now this is the best FPT algorithm. 2 is the best approximation ratio. Can we improve? So it seems like 1.27 in the case is going to be a complete pain to improve. Okay, and 2 as the approximation ratio also seems like a bit of a glass ceiling. So can we say that? Can we think about coming up with, like, give ourselves a little more than poly time, but not so much time, like less than this time, and get a better than 2 approximation. So the FPT people have always looked for exact solutions, and the approx people have always looked for polynomial running times. Okay, now what we are saying is convince the approx crowd to like loosen up on the running time, and tell the parameterized people ki thoda approximation chalega, adjust kar lo, okay? So now we want, like, in some sense, the best of both worlds. This is probably not, okay, so more compelling use case is when there are problems that are actually hard, like in the parameterized world and in the approximation world. Like there are really no good approximations and no good parameterized algorithms. That's when it really makes sense to combine these paradigms and at least get something. Okay, and even in that setting, there's this sort of a lot of new hardness frameworks that show like some problems are just really heat, you cannot do anything at all. Okay, so there are such situations too. But yeah, this is like a nice question to think about. So let me just give you like the high level idea, because I do want to spend like 10-15 minutes on partial vertex cover, which is like also a nice problem. So okay, so the algorithms that we have seen for approximation use matching. So let's say this is some maximal matching. Okay, so if I pick everything, I get a 2 approximation. But now let's say I don't pick everything, but I pick some. Again, I picked L of my favorite edges. Okay, and now how many do I have left? Okay, this matching better have at most k edges. If the matching has more than k edges, I can say no, because more than k edges definitely requires vertex cover size more than k. So how many edges do I have left here? I have k minus L edges left here. So let's run 1.27 to the k minus L. So if I pick L to be something like k by 2, okay, what do I get? This running time is going to be square root of 1.27 to the k. Okay, this part was anyway poly. And what is the result? The result is like yahan pe I may have picked k by 2 extra vertices. So I'm off. So the guarantee I have is at most k minus k by 2 plus, so this is plus k. So this is 2k minus k by 2. Does that make sense? So this plus k is coming, this k minus k by 2 is coming from the fact that here, okay, I'm looking for a vertex cover with this budget, right? So I either get that exactly, and yahan pe this is going to be k because it's going to be, I'm picking both endpoints here, right? So you get this kind of sweet, better than 2 approximation and better than 1.27 to the k time. So you can imagine that tweaking that choice of L will give you different trade-offs. Okay, so that's kind of the high-level idea of how you combine ideas from parameterized and approximation. I'll give you a slightly more non-trivial example in whatever time you have left. You have some time left? Okay, alright, so can we switch over to this one? Because I don't think the board will be super efficient, so
Let's see if I can manage 2 minutes. It'll be good.
yeah, okay, awesome. Should we try to switch this up?
Did that work?
Let's see. You're about to find it.
Okay, good. Worked.
Okay. Okay, so in the last part of this session, we're going to talk about like basically a similar framework, and we're still not letting go of word discover, but we're going to talk about partial word. Okay, so you're going to do partial word discover, where along with the budget K, you now have a new parameter which is T. Okay, and T is, so you can't always have everything. So maybe K vertices are simply not enough to cover all the edges. The next best thing you can ask for, if you're fixed on the budget, like the budget is a hard limit, is you can say, okay, given this budget, what's the largest number of edges I can cover? Okay. So again, if you were writing this optimization style, there are many ways you can write this. Like you can say, can we cover at least T edges with what is the smallest number of vertices we need to cover at least T edges? So your target is fixed, you're willing to vary the budget. Or you could say, given K vertices, what's the maximum number of edges I can cover? So that's another optimization question. In this case, I'm just making it like explicit on both fronts, okay? It just makes it a little easier to talk about, but you can certainly optimize on one of these parameters and keep the other fixed. Okay, so if you're trying to optimize on the t-axis, then the best known approximation is 0.9, and this is, I believe we know that this is the best possible, I think. And now there is also, like, the parameterized people have their own hardness theory, which tells us that you cannot solve this optimally parameterized. I think parameterized by k. I hope I got this one right. So I think it's doable with one parameter but not the other. So, okay. I also made these slides last night, so double check. so don't take them too seriously. But yeah, okay. So essentially these are the sorts of parameterized approximation goals that we have. So so here actually we have a flexible. I mean, since there was something about approximation schemes, I'm going to just briefly touch upon the idea of what it means to have an approximation scheme. Is to say you pick your own approximation ratio, but pay the price in the running time. That's roughly what it is. Okay, so here pick your epsilon. Okay, and I get to cover like so we're approximating on the t-axis. So if you want to cover 90% of the edges, then you're going to pay some price in the running time, some appropriate price in the running time. So you can get as close to t as you want, but there is a trade-off that shows up in the running time. And there is like also a +1 approximation that I actually will not get into, but it's good to know that you can cover t edges using FPT time, and you end up with an additive +1 approximation. It's also something that you can actually do. All right, so okay, I think I wanted to say here that I phrased these as find these things, but you could very well be dealing with no instances. So of course in this context, your algorithm is allowed to say no if it's confident that it's a no instance. So you always have that out. But if that's not the situation, then hopefully you're able to output something approximate. Okay, good. All right, so okay, I meant to prompt you on this, but I'm sure this is what you would have said if I asked, like, what's the first thing you would do if you want to pick a small number of vertices to cover a large number of edges. You would want to pick the max degree vertices. I think it's something you said way back in the first session of this course, so this makes sense. Let's rank the vertices by their degree, high degree vertices showing up first. Okay, so what's the problem? Like, why can't we just return like the top k vertices on this list?
Because the first two vertices can, they can have like a lot of connections with themselves.
Okay.
So I think the procedure that we need to consider is that take the first
vertex which has max degree, remove all these edges and then reorder this again.
And then reorder again. Yeah, sure.
Sort
Yeah, that sounds like a nice sophisticated thing to do. We will do it probably in a problem solving session. So we are kind of going to, we're going to see how much we can push this naive idea. Okay, so yeah, so basically the idea was to say, you know, if the top, even the top K heavy hitter vertices are not able to cover T edges, then who's going to do it for you? So just say no, okay? So yeah, so this doesn't work, and the reason is what was already mentioned. The problem is that you can have a lot of edges sitting inside. So even though these guys are heavy hitters, they're not projecting all their edges outside. They're friends among themselves, and so the degree is not getting fully accounted for. Okay, so if you think about that a bit, it will hopefully become clearer. But let's think about like what can we say about T? So let's look at the top K vertices, and can we at least say that the sum of their degrees is like, you certainly cannot do better than this. Is that reasonable? Because if T is more than the sum of the top K degrees, what can we say? You can say no? Yeah? Because take any solution, right? Take any solution, your favorite solution, your optimal solution. Even the optimal solution, the most it can do is the sum of the degrees of the vertices it has chosen. If anything, it will be worse because some of these edges are actually going inside and they're getting overcounted, so their real contribution is less. But you know, even if you're like a complete optimist saying sare edges bahar ja rahe, then even then you can only do sum of degrees. And if you can only do sum of degrees, the best hope you have is the top K guys, right? So the top K degrees ka sum is definitely like an upper bound on opt. Okay, if you're thinking about optimizing on T and K is fixed. Okay, so yeah, it definitely feels like T is at most this. And if you look at the top K guys, what guarantee can you give me? Like if I say, okay, pick the top K guys, they surely cover at least these many edges. They surely cover sum of degrees, not quite, because some things are getting gobbled up inside. But how many things can get gobbled up inside? KC2, right? We can't be overcounting more than KC2, right? So sum of degrees minus KC2 though we can manage, right? So this is hopefully clear, right? So these fellows are the overcounted edges. So in the worst case, you know, your top K friends are forming a clique, in which case you're losing a lot, but you're not losing more than K choose 2, okay? So basically, if औकात के बाहर T है, then say no, right? Because if it's exceeding sum of top K degrees, say no. But if T is less than this, then you already have this, so you can say yes, and you're happy. So the tricky thing is when T is in this range, then we don't know what to do. Okay. All right. So if it's smaller than the left-hand side, say yes. If it's larger than the right-hand side, say no. If it's sitting in between, we don't know what to do. Okay. All right. So. Okay, so now remember goal number 1 was to come up with some sort of a epsilon T kind of a solution. So if we can, basically now we are upgrading our statement to say that, okay, look, if the top K guys cover at least an epsilon fraction of T, then also we are done, okay? So the question we want to ask ourselves is, when can we say that the top K guys cover an epsilon fraction of T? Okay? So of course you can just look at it and check for a given epsilon. But I want to do some thresholding so that I can say, okay, if the value of K is something, then I can just say yes. Otherwise, something is bounded and I can make progress, okay, something like that. Okay. So we want to dig a little bit deeper into this inequality here. So I'm going to say that the top K degrees minus K squared. So by the way, I'm like K choose 2 was too lazy to write, so I'm subtracting a little more, but that's okay. Yeah. So now remember that T is at most sum of top K degrees, yes? Because we just saw that earlier, right? If T is more than the sum of the top K degrees, we said no. So T is at most the sum of the top K degrees, so we can write this, yes? Okay, so now what this means is this we have just divided throughout by T, so that's reasonable. And now the question is, what kind of a threshold can I impose on? So can I say that if, okay, let's even try to just get the direction right. So if T is very big relative to K squared, then is this inequality likely to hold? Like if T is, I don't know, like K to the 100 or something, yeah, then 1 over k to the 100 uh, is really tiny relative to k squared, right? So, so what are we doing? We are taking out. So is that a good situation? Is that a bad situation? It's a good situation. Yeah. Okay. We are taking out a small amount, so we are likely to be okay. Yeah. We have to. Okay. So. Yeah, okay, so there's an analogy that I'm going to borrow from one of Saket's lectures on this topic, and you can think about it if it makes sense. His point is that he's thinking about what you're removing relative to the overall size. So you're always removing a bucket of water. You're removing a bucket of water from an ocean, nobody's going to notice. When you're removing a bucket of water from a tiny pond, then you remove a few buckets and you might dry out the pond, so you have to then be careful. But if you're removing like a bucket of water from a very large space, then it's not really going to matter. Okay? All right. So so with that sort of intuition, so what we are going to say is, okay, so suppose t is some xk squared, right? So then we are looking at, if you plug this in, you're going to get like 1 minus 1 over epsilon. And if you want this inequality to hold, you want the coefficient x to be at least 1 over 1 minus epsilon. Okay? So if you can see this, you're amazing. If you can't, you're also amazing. It's okay. Just like, it's just a little bit of rewriting and you should be convinced that this is okay. So again, because we want to get to the end of this, let's just like believe this for now. Okay, so essentially as long as t is at least 1 over 1 minus epsilon k squared, this inequality will go through and we are happy. Okay, so we are now thinking of t as a threshold and as a function of k squared, so this is fine. Now the remaining case is then when t is at most k squared over 1 minus epsilon. Is that okay? Like it's the opposite of what we have here. Okay, all right, so okay, so now in some sense t is at most something, and we're going to lead with this. So now what we are actually going to do is say, temporarily let's forget about the epsilon business. But we're going to, so we've done all of these kind of initial sanity checks, and it's come down to this. It's come down to this situation. So now if we can design a nice algorithm in terms of t, like some f of t poly n, then we are happy, right? Because then the running time is some f of k epsilon, right? Because t is bounded by some function of k and epsilon, right? So if you can come up with the f of t poly n algorithm at this point, you're happy, because you know that either you can finish off the instance directly because of bounds, okay? And if you can't finish it off directly, then t is bounded as k squared over 1 minus epsilon. So now if you have a f of t algorithm, f of t poly n algorithm, you're basically happy, yeah? Is everybody with me so far? Yeah? Okay, good. So, all right, so this is like silly opening at this point, but if you have a vertex whose degree is at least t, what do you do? Yeah, okay, you just pick this vertex and you're immediately done, right? So k is at least 1, so you're done. Okay, so what does this mean? This means that this graph has bounded max degree, right? Okay, so the max degree of this graph is at most t. Yeah, here you again directly say yes. So now we're doing this FPT in T kind of algorithm. So by the way, FPT, I don't know if I officially introduced you to FPT, but yeah, f of k poly n is FPT. Like n to the k is not FPT. Okay, so yeah. Okay, f of k, so where the polynomial is fixed and independent of k. So that expression that we have written down, those are called fixed parameter tractable running times, because when you fix the parameter, the running time becomes tractable. It's a little cheesy, but FPT. Okay, all right. Good. So the max degree is bounded, and now let's just do a little more. I think you can probably get away without this, but just for fun, like if k is at least 2t, what does this mean? This means that okay, so you are using you have to cover, let's say 20 edges, okay, and k is at least 40, okay, which means that these 20 edges can be like really spread out, like so 20 What's the natural graph that comes to mind when you're thinking 20 edges, 40 vertices? A matching, right? So that seems to come to mind. So if you have this kind of luxury, right, that k is at least 2t, so you have lots of vertices to cover a small number of edges, right? Then you can actually use a matching, right? So let's find a maximal matching. Now what can we do with this? Well, if the matching has t edges or more, okay, then you can just pick any t edges from the matching, okay? It will require 2t vertices, but 2t don't have number different. K is at least 2t, so you can just pick. So if the matching does not have at least t edges, the matching has at least t edges, we are done. The matching does not have at least t edges. The size of a maximal matching is at most t. तब क्या करोगे? Yeah, just take the whole matching, right? Just grab the whole thing. You've covered every edge that there is to cover. Okay. The graph only doesn't have t edges, then that's a different problem. Okay. but like you've literally maxed out on what you can cover, right? So the matching is big, then pick any t edges you want. If the matching is small, then you have a small vertex cover. It covers all edges. Okay. So this is okay. So now we can assume that k is at most, or in fact strictly less than 2t. Okay, good. All right, so this is something that we are just going to remember to bring back. If the maximum degree is bounded, then by Brooks' theorem you can color it with, not bound many colors. Okay, so we just talked about what proper coloring is earlier. So if you don't know Brooks' theorem, just believe it for now. What choice do you have? So okay, so any graph which is not like an odd cycle or it's not a complete graph can always be colored with max degree many colors. Okay, and for odd cycle and complete graphs, it's like max degree plus 1. So for an odd cycle, it's like the max degree is 2. You can do it 3. For a complete graph, you just need to give every vertex its own color. Max degree is n minus 1. You use n colors. So in general, well, max degree is strictly less than t, so I can surely color this graph with t colors based on Brooks. Okay, all right, fine. So this is t colorable. Let's just keep that in mind. Okay. All right, so now let's focus on hypothetical yes instances, because that's hopefully the sort of instances we are working with, because this is like with iterative compression. We go in being optimistic, and if all our yeses fail us, then we can say. Okay. So suppose you have a yes instance, so there is some set with k vertices that covers at least t edges. Then what can we say by pigeonholing? There must be some vertex in S whose degree is what? Greater than k by t, at least k by t, because if every vertex falls short of this degree bound, right, you won't be able to put them together and cover these many edges. Right? Okay. All right, so this for sure, right, at least t by k. Everyone okay with this? Right? Okay, so this is just averaging or pigeonholing, whatever you want to call it. So let's collect all the high degree vertices in our graph. Okay. These are all the vertices that have degree at least t by k. What do we want to do with these guys? I want to say that if there is a large number of high degree vertices, then we are actually good. Otherwise, the number of high degree vertices is small and we can do some branching, some exhaustive recursive thing. Okay, so if I have at least tk vertices, tk high degree vertices, then I am done for the reason that, okay, we have to put 2 and 2 together coming in from Brooks' theorem. So if I look at this coloring with t colors, okay, so if you have colored, so I have at least tk high degree vertices. Now G can be colored properly with using just t colors. So in particular, the high degree vertices get partitioned into t color classes. Right? Altogether, there are more than tk vertices. So some color class must have, must have at least k more than k depending on the inequality, right? So some color class must be large. But why do we care about color classes? Because color classes are independent sets, which means all this degree is getting thrown out, right? So nothing is getting gobbled up inside, so we don't have that problem. So if you have k vertices all of which are high degree in the sense that their degree is at least t by k. And when you look at the subgraph induced on them, that's independent. That means these k vertices are actually covering d edges. Okay. So when this fellow is big, you're actually done. I know. Stopping. I thought you were looking at the clock, so I'm saying I'm stopping. Oh, good. Okay. All right. So, oh, I see. Okay. Sorry, misunderstood. Okay. So, all right. So if I have a large number of high degree vertices, I can use Brooks' theorem to say that there must be some large color class, and that must be a large independent set, all of which has high degree. So this is very good for us. We have k vertices that cover t edges. So we're done. Otherwise, H is less than Tk, okay? But we know that our optimal solution must pick at least one high degree vertex, okay? So now we can guess, and we can afford this guess because this is going to be only a Tk wave branch, okay? Yeah, and I guess this Tk, again, depending on how we want to bound it, this is actually 2t squared because k is at most 2t. So we can write down everything in terms of t if we wanted to. But yeah, so the idea is that you recurse. So this is a tk branching width, and then we're only allowed to pick k vertices, right? So the depth is again going to be at most k. Okay? And at every stage, basically, you have a fresh instance, so you do all your sort of simplifying things. If you can solve an instance from these simplifying phases that we had earlier, then you can just percolate it upwards. But otherwise, you come back to this situation and you can again do a small branching. So yeah, so you can recurse and you can convince yourself that this whole thing finally works out. So I think this is actually the overall algorithm. So yeah, the top two rows tell you, like the top two lines tell you, like the very first bounds that we had. So if t is too big or t is too small, we are done. If it's too big, you can say no. If it's too small, you can say yes, relative to the sum of degrees minus k squared. Now, in terms of the epsilon t target, we saw that if t is at least k squared over 1 minus epsilon, then actually the top k high degree vertices in the graph actually cover epsilon t many edges. So then again we are done. Otherwise t is bounded. When t is bounded, then we dug in a little bit more to say max degree is bounded. That we did because if there is a vertex of degree t, you're immediately done. So max degree is bounded. And k is bounded by 2t because otherwise you can use a matching to get what you want. Now we said, well, let's focus on the high degree vertices, and if that's a big set, you can use Brooks' theorem combined with the max degree bound to say that, okay, look, you have a large set, all of which has high degree, the large set is independent, so again you're done. Otherwise, finally, you're stuck in a situation where like everything is nice and bounded, so you can afford to branch. That's basically what's happening. So you have an f of k epsilon time, you have epsilon t coverage using k vertices. So this is a FPT approximation scheme. FPT because you're using FPT running time. It's an approximation scheme because you can pick your epsilon and get as close to opt as you want, where in this case, opt is the number of edges that you're looking to cover. This is not the latest and greatest on partial vertex cover. I think you can do sort of better by using some other randomized techniques, which can also be de-randomized. And I think there's a paper of Marx which does. Yeah, I don't know which ones. Yeah, off the top of my head, don't know if I. So there is definitely an algorithm that uses from when you say that the max degree is bounded. From there, you can do some randomized coloring and de-randomization, and that's going to be another approach to doing partial vertex cover. So for those of you who may already know what randomized separation looks like as a technique, it's a very nice exercise to work that out for partial vertex cover. If you haven't seen random separation, it's a really sweet technique, and I'd encourage you to go look it up. So what I'm going to do is share with the organizers the slides and some pointers to other resources on FPT approximation. Hopefully you're sold on the idea, and the good thing is it's a relatively new theme, so lots and lots of things to do in terms of open problems, trade-offs, and things like that. So learn a little bit of FPT, a little bit of approximation, and then start combining ideas from both, and may the power be with you as you do that. Okay, so I think I'll stop here, still in time.
Okay, so He has managed to be on time this time. And we have a photo session outside, I think.
Okay.
Hopefully.
Yeah.
See you
Alright,
soon.
so photo session after this, yes, okay.
And then we'll have the tea.
Okay, alright, thanks very much everybody. No. I can do a little bit.